Good afternoon. So thanks ever so much for inviting me. I've spoken an awful lot of really dull BIM conferences over 5-6 years. I've never been to one actually where the quality and the consistency of the speakers has been so fantastic. So it's been actually really fascinating for me to sit and hear some of the other things that are happening in the industry. So I'm going to try not to bring the average down too much. So who are Bryden Wood? We started out 22 years ago as a firm of architects. So I'm technically an architect by training. It's increasingly hard to tell anymore. We always had a real interest in design for manufacture and assembly. So we were specifically set up to answer this sort of question. So everyone's got their favourite statistics for why construction's so crap. You've seen the productivity one's been mentioned a couple of times over the last couple of days. You've seen the statistics for numbers of projects that go over budget, over time, et cetera, et cetera. These are my favourite statistics. This is from a big trawl that one of the main government departments in the UK did on all of its projects over its framework, and it found that these are the big hitters in terms of projects overrunning in terms of cost and delays and. You can see the big problems are poor productivity, we've talked about, labour shortage, lack of materials, lack of information. So if you could get the right things to the right people at the right time with the right information, that's a significant chunk of the problem sorted. So come on, construction, we can do this. This is another one. They looked at how much of every pound they spend ends up in residual asset value. I suspect this is not atypical for lots of clients. Only about 50% of the pound or dollar they spend on a project ends up in actual value. The rest of it disappears into all of these other things. So a sort of traditional value engineering exercise would be to squeeze the supply chain and try and eke out a few percent. Our thinking has always been, forget that one, that's a massive chunk to go after. If you could start driving down the percentage of non-value adding activity, that would be a huge step forward. Those are those arranged in order. So product is 50%. Client risk is the next biggest one, which tells you something about the state of the industry. Then you get overhead on overhead on overhead on overhead, because you get the multiple tiers from main contracts all the way down. We've been reorganising this traditionally and saying, right, we will absolutely optimise the product. So this is what manufacturing does really well. The car industry, aerospace for years have been shaving grams off components, taking out activities in the manufacturing space, just making incremental changes that make the product ever better. We think, it's gone. So we optimize that, we protect this. As I say, clients very often try and squeeze a few percent out of the supply chain. If you do that, they will hate you, and they will get that money back because they will gouge your eyes out on every single change order. We've been saying to clients a much more sensible thing to do is protect people's profit, be very open book, make sure people get paid well for the work they do. That will enable the behaviours that then allow you to move things forward. The next one down, we try and reduce fees. So for an architect telling you that we're trying to reduce design fees is a bit spooky. It's actually been a sort of recurring theme over the last couple of days around the use of tools for automation, spending more time on the really value-adding bits of the design, not on the churn of door schedules and pulling things out. So we're trying to actually overall reduce fees by learning on projects and doing things better each time. So ultimately it becomes quicker and easier to design buildings, and we'll show you what that looks like. We're then trying to massively reduce overhead and overhead. We did a study on steel. Raw steel from a manufacturer costs £300-500 a tonne. By the time it's on site, it's about £3,000 a tonne. So the client has paid for every factory amortization, because it starts from the manufacturer, it goes to a stockholder, then it goes to the fabricator, they do some work, then they send it to the MEP guys, then they put some stuff in it, then they send it to site, then it lays around for a bit. So materials start to accumulate cost as they go through this process. Doug yesterday talked about if you had an absolute focus on speed of assembly, you would start to change the whole design process, you would start to do things very differently. Our equivalent is focusing on asset value, residual value, and saying the closer we can get to raw commodities, the closer we can get from literally raw material gets touched barely at all, and then it's a building, that will start to drive out huge chunks of this. It will start to get enormous value. It will start to change the way you design your buildings. And then the bottom one, we try as far as possible to eliminate this. So we do an awful lot of testing, prototyping of systems. Typically on our buildings, by the time we get to site, there is nothing left to learn. People are not there measuring, scratching their heads, wondering what to do. People are following a series of instructions and assembling assets, and we'll show you what that looks like. So this is a snapshot of 22 years of different systems we've developed. By complete coincidence, that's Madrid's global switch data center we did back in 2002. That's Heathrow Airport. So you can see sometimes we do these big modular boxes. So where the client driver is all about absolute speed of assembly on site, that's the sort of solution. That's post 9/11. This is pier segregation for Heathrow. That's our building site. We've got 2 people, crane driver, banksman, airside, so risky environment, overnight, so you only get a few hours to work. And these guys are absolutely throwing these buildings together because all the work happened off site. The last phases of this were built, we set up a factory near one of the airports. These were built by completely low-skilled people we literally got from the job centre. So just in the way that Jaguar Land Rover cars aren't made by skilled mechanics and engineers, they're made by people who are trained to do specific tasks. We are taking literally people off the street, training them up, and they are building quite sophisticated buildings. This I might talk about a bit later. That's a water infrastructure project. So again, for a team of architects to be, some of the biggest gains we're making at the moment are in infrastructure. So we're coming into water, rail, roads. The fact that we're architects, people assume you can't possibly know anything about roads and rail, which is actually a good thing because we don't come with 30 years of doing the wrong thing. We come in with a very refreshed attitude saying, why do you always do that? What's the principle? We get very quickly back to first principles. So this project was transformed from what would have been a heavy civils project, because it's water, so you dig a fucking great hole and fill it with concrete. That's what you always do. We did a quick study early on and showed that if you bought a pump, you could run the pump for 9,000 years continuously and it wouldn't cost as much as digging the hole, remediating the soil, filling it with concrete, doing all the rest of it. So suddenly we just elevated the thing out of the ground, then it becomes a petrochem type facility, then you can start to DFMA it, and it just completely transformed that project, and it's been one of the most successful water infrastructure projects. So there's a whole range of systems on there. You can see we have a real mix of sort of volumetric, we do componentized buildings, we do steel, we do concrete, we do timber. So we don't have a particular system that we're trying to foist on people. We have a whole palette of techniques, and depending on what the project is and what the client drivers are, we will start to develop quite specific solutions. The other thing on that to notice, that was our factory. So for about 10 years, was it 8, 10 years, we had our own factory, which sort of came about because we got really annoyed with the industry not keeping up with us. So we started out as architects in 1995. By shortly after 2000, we got our own mechanical, electrical, structural engineers, because we had to have all the disciplines to do the things we wanted to do. We then started prototyping, those are the 2 Simons, prototyping some of the systems that we wanted to do, because again, we got annoyed of designing things that the industry said, you can't build a building like that. And eventually we got our own factory because we just had to completely own the process. We don't have the factory anymore because we'd sort of proved the point. We didn't need to manufacture things as much, and we now have a series of facilities that we use on and off to prototype systems. So we're much more likely now we develop a system, prototype it, test it, learn everything there is about it, and then we go out to the market and say, right, I'm not asking you to design anything, I'm asking you to do this activity 10,000 times absolutely perfectly, and it's a very, very different way of procuring. So I'm sure you'll get these slides, so I won't go through it, but you can see some of the sorts of metrics. So firstly, this is all sort of different sectors, so hospitals, airports, pharmaceuticals, schools. These sorts of numbers, 20% quicker, 28% cheaper, 38% quicker, lots of people off-site. We just keep getting those metrics. We would typically back ourselves now to take 30, 40, 50% out of cost and program for almost any project. These are some of the big modular things. That's that data center stuff at the airport again. You can look at those later. We've almost always worked in a very 3D environment. So the reason I got involved in the BIM task group when Mark Bew and the team started setting things up, we were one of the very, very few people that had actually been doing this for a long time. So we had an awful lot of expertise around using not only kind of software authoring systems, but also sort of data visualization platforms. We use a thing called Lana Witness, which is software. It's typically used in manufacturing to model manufacturing processes. So we don't just have the kind of design authoring software. We bring a whole load of different skill sets to bear. One of the biggest growing teams we have at the moment is they're sort of mathematicians, financial analysts. We've got some chemists. We've got a geophysicist. So some of the people we're employing now are just not at all construction people. They are just bright people who can work very complex problems. So we do increasingly kind of very front-end data analytics, data modeling now. If you look on the website, these are the capabilities we talk about. So we've got still the traditional design disciplines. DFMA sits fairly centrally. Systemization is like the big brother of DFMA. So if you want a one-off project, you want some DFMA. If you want to build Crossrail or a series of hospitals or the big justice estate, you need systems. So we do an awful lot of work in this space now, generating sort of mass customizable, flexible components that we can generate very site-specific, very individual buildings, but using components that are almost completely standardized. So just as every person is completely different on the outside, at DNA level, we're incredibly similar. Process facility is some of the kind of complex pharma things we'll talk about. Design for asset optimization is a thing where increasingly now, this has been talked about over the last couple of days, we get called in by clients or contractors to fix designs that are non-constructible. So very often, clients get a design in, it's just too expensive. We get called in to re-coordinate it, rework it, turn it into a DFMA type thing. So I'll show you what that looks like for Crossrail. And ops consulting, we got to a point probably 2008, 2009, where we were saying to clients, look, we know that if you want a building, we'll nail that. It'll be quick, it'll be cheap, it'll be very high quality, it'll be manufactured. We could still do a fantastic job of building completely the wrong thing because you as a client don't know what you want. So we found lots of clients effectively write the brief by building the building and then knocking things about through the construction process and then making lots of changes and then ultimately getting a building going, yeah, now I can tell you what I want. It's not quite this. So we started moving earlier and earlier in the process to say, actually, don't tell us what the brief is. Tell us what the problem statement is, and we'll help write the brief. We'll develop the brief. Then we can design a building that won't keep changing through the design process. Then we can start to componentize it. So we ended up with a methodology we call chip thinking. So we found with particularly complex client organizations, so GlaxoSmithKline, healthcare people, they have a whole load of different stakeholders. They all look at the business through a really specific little lens. So they're sort of subject matter experts on one tiny bit of the problem. They very often don't talk to each other. They very often don't know the others exist. So we started breaking buildings or processes down into sort of value-adding or transformational activities. We then started finding out what every single person in the business knew about that particular aspect. And the idea was like chips on a motherboard, that you could aggregate loads of information around or insight around a particular thing. You could plug a load of them together and then you could see what happened and you could see how buildings started to work. So a healthcare example, at one level, we'll model every single nut, bolt, screw and piece of medical equipment in a theatre. At one of the chip levels, a theatre never exists on its own. It always has a clean core, an anaesthetic room, clean and dirty circulation, some plant that comes with it, a digital hub. So that's a sort of cluster of things that always happen together. So you can start to break buildings down into clusters of activities like that, start to learn how they work, and then start to put them together and test a bunch of hopefully very visual kind of data outputs. So these are all the sectors we work in. I'm not going to talk about all of these. I'm going to explain the pharma stuff because it's a fairly quick way of showing sort of end-to-end the sorts of things we do. I'm going to talk about rail and highways just because they're some of the more sort of digital to physical linked things we're doing at the moment. So this is a good example of a problem statement that clients come to us with. GlaxoSmithKline have a initiative to get to 80% of the African population by 2020. So that was the question. They came to us and said, Africa, what do we do? We've now got to a point in our office where we've got an entire floor of the office that we literally give to clients. So we give people free space in our office to come and work from the office. So we started doing people saying, why would you want the clients there always looking over your shoulder? We were saying, I guarantee you the gains we'll get in terms of productivity and our speed of iteration by having the client there will more than pay for the space. We don't mind clients seeing what we're up to. We'd rather be very transparent about it. And we found now that we have a completely permanent presence of GlaxoSmithKline people in our office. Adam heads up our Singapore office, which was largely set up to work with the Asia Pacific GlaxoSmithKline people. So we have this sort of nice relationship now where the team that's set up, it's impossible to tell who's one of our people, who's a Glaxo person, who's a chemist, who's a specialist in a particular piece of production, who's a logistics person. And the speed of iteration, the speed with which we work these problems is now absolutely lightning fast. So for this exercise, we did effectively mathematical models describing population centres, infrastructure, geopolitical stability, transportation, logistics. We started churning lots of options around, do you bring in finished product and distribute it? Do you bring in raw materials and make it? Do you bring in finished things, package them? What do you do with Africa? What's the mix of products? Where do you make them? How do you build them? Which has been enormously successful. At the next level down, one of the things we very, very often do, Adam gave me a great example just now actually, one of the things we very often do is convince people not to build a building. So Frank mentioned this yesterday, the idea that the best building you'll build is the building that you don't build. So this was an example where the assumption was a whole new asset was needed. We went in and we measured the intensity of the usage of all the different spaces, and then the types of capacity, types of capability, what they did in those spaces, and worked out that you could upgrade some of the MEP equipment, you could make some of the spaces a bit multifunctional, you could get a room booking system, and you could wring out quite a few, do you know the numbers? Quite a few percentage of extra capacity from exactly the same equipment, exactly the same machines, people, all the rest of it, just by organising things differently. So we very often now get people, you get the project sponsors that got the £50 million check. It's the only time in their life they'll get to commission a building, and we're saying, I wouldn't do it, just wouldn't build it. We got audited by McKinsey a few years ago now to come and look at all the stuff, because Glaxo were making some really big decisions based on our say-so, based on some fairly young people doing some stuff on Excel. Actually, McKinsey audited us and said, they call it best-in-class consulting, and said the most valuable things we had done were things where we'd convinced them not to do a project, and then 6 months later, lo and behold, population growth wasn't working the way they expected to. The market was moving away, generics were coming in. So we've got loads of case studies now. There's another one, I can't tell you the details of it, but you reckon you've saved 39 million quid this morning from convincing them not to build a new asset. So this is really powerful stuff now. What it does mean actually is that when there is a project, everyone sort of trusts us to do it because we've gone through all the iterations. So next level down is the individual chips for piece of equipment. So we typically have, we've got now certainly hundreds, probably thousands of these chips for probably every type of process that you need in the pharmaceutical space. We've got a library of chips for healthcare. We've actually got a chip library for justice now. We've got a sort of series of these chip libraries that we deploy. So typically we have a little model. More importantly, we have every bit of data, including things like the numbers of people, the types of people associated with that piece of equipment. One of the big wins we had early on was we started attributing utilities to individual chips. So there was a particular site that Glaxo had where it used tons of water and electricity, and they kind of split the bill by 5 because there were 5 products. When we really started looking at all the processes, we worked out that one of the products was using most of the electricity in the water, and it wasn't nearly as profitable as anyone thought. And it transformed the product mix going into Africa. Obviously, they don't want to make a thing in Africa that needs loads of water and electricity. So just the fact we started pulling these things apart, we'd said to Glaxo fairly brazenly back in the day, I mean, now I'd say we know lots about pharma. At the time, we didn't. But we had a guess that we would be able to explain to Glaxo more of their corporate knowledge about any topic than anyone in their business, which is a fairly bold thing to say. But because of this process of really collaborating, really dragging people's knowledge in, we're actually able to do that quite successfully. So that's a typical chip. Sitting behind that is as much data as we can get our hands on. Some of it's guesswork, some of it's really well-structured, validated data. We'll take whatever we can get our hands on. So we get a real mix of things that are, finger in the air estimates down to things which are, measured on a day-to-day basis. But chips are a really nice sort of repository for anything we can get our hands on. And then we plug them together. You can test endless different scenarios. You can start to try out lots of different, we've talked about sort of machine learning, generative design. This is all the sort of stuff we do with chips now because they're a sort of useful data-rich repository. You've kind of seen some of this stuff earlier. I was going to talk about sort of process flow diagrams, which are captured in Excel. Script it in Dynamo, and then we start to get generative models for complex processes. So a lot of the stuff we're doing now is, or some of the stuff we're doing now is in biopharm. So this is emerging technology. So we're designing buildings for processes that no one knows what the process is. No one really understands the chemistry, and probably the kit hasn't been invented. So you've got to build a building for this sort of complete unknowable world. So we just start generating these basic models. These have got loads of parameters, and every time you know a little bit more about the process or the equipment, the model updates itself around it. So we end up with these. This is actually a precious metals refinery project. So these are various processes, and every time you learn a bit more about any of those things, the entire model flexes around it, and you get to the point where the process is done, and then you slap a building over it. So increasingly for our clients, the sort of it's been known for a long time. The sort of construction cost is X. The FM cost is probably 4 times bigger over the life of the building. In healthcare terms, staff costs are then 3 times bigger, and then the business outcome is however much bigger, and then the societal outcome is enormous. So actually construction cost is a teeny tiny bit of the value chain if you look at what buildings are doing. GlaxoSmithKline happen to need buildings to put the processes in, but their business is healing the world, fixing the world. So I like the quote that Shane had on the screen earlier about the factory is the machine for making the machine or making the component. We spend loads of time really understanding the process, optimizing the process, planning all the future flexibility, all the rest of it, and the building sort of reveals itself late on in the process because it's actually the last thing that you need to do. If you spend, the more time you spend on the machine, obviously the better the outcome is. So that's a quick summary of chip thinking. So we get data capture. Yesterday people were talking about LOD, LOI. So this would be sort of LOI, I don't know, through the roof because it's got endless chunks of data, but it's completely geometry poor because we don't really care what the components look like. So this is a series of chips. This is things come in, they get stored, they get turned into products, they get stored, they go out the door. You can imagine at this level, we can run endless iterations around, do you have fewer vehicle movements, more storage? Do you have less storage, more vehicle movements? What happens if you add a line? What happens if you add a new process? So very often we don't try and design sort of a solution. We design a search area of solutions, and then we gradually converge on the answer. The other thing that's quite nice about these, some of these will be chips that have like really well-known data measured from existing facilities. Some of these will be chips that don't exist. So you can drop into this a chip that doesn't exist and say, if you had a chip that did this, this would be the impact on your business. You need this chip. So let's trawl the market, we'll talk to Siemens, we'll talk to GE, we'll start to work out whether you can get a chip that does this. So in our library, we've got some chips that are real chips, we've got some chips that we kind of made up, we've got chips in different stages of development, but you can sort of drag them all in, and the ability to work again with kind of the real and the unreal at early stage is quite powerful. And then we generate, again, hopefully very, very visual outputs that explain, this is looking at staffing costs, this is predicted. So bear in mind, we're nowhere near designing a building yet. We can tell you how much it'll cost to run the facility when we have designed it. So the ability to kind of future investigate utilities costs and things is incredibly powerful. The other thing we very often do, you can't read that, but these are sort of faded out because this is the staffing costs we think you need today, and then this is our guess at what the staffing costs look like in 5-10 years. So very often now we're not designing a building, we're designing several phases of a development. There's the building that you can afford now, and then there's the building that we think the business needs probably in the future. So these are the sorts of things we get out of it. Faster option appraisal, because we have the client on side. You don't ping them an email and wait a couple of days and then they come back and then we have a chat about it. You literally drag them and go, we're about to change something, come and tell me the answer to this. Joint decision making, because everyone can see how the thing that they've contributed was embedded in the chip. They can start to understand exactly how their bit of the puzzle relates to everyone else's. We started doing a thing which was really powerful actually, where we started naming individuals who had told us anything and then color coding the quality of the information. Because what we found is you go and talk to a subject matter expert, you'd ask them a bunch of questions. Some of the answers they would give you would be things they absolutely know because they've done it for 30 years and they know that's their bread and butter. Some of the answers would be complete guesses because no one's ever asked them the question before. What we found when we started running the chip models is you get some really bizarre outcomes. So we said to GSK, it's fine to guess as long as we know you're guessing, and we'll tell you whether it is important or not. So when we twist all the dials, with certain things you can do that and nothing happens, you go, right, you can be out by a factor of 50, doesn't make any difference. There'll be other bits that are incredibly sensitive. So we start saying, right, let's do more investigation on this topic, let's find out more about a particular thing because it's actually really critical, which means that we don't have to have a sort of blanket 10, 20% contingency. We have very, very specific things that we know are known risks, and we can work through those. We get better procurement, and I'm going to talk about that in a little bit. As I say, we very often now design multiple phases of buildings and help clients make better informed decisions. So we very often say, look, we think you'll need tons of power and water in 5 years. You can either invest now and over-specify resilience for power and utilities, or you can leave it and know that in 5 years you've probably got a problem coming, but at least you know you've got a problem coming and we can work through it. So it makes clients much better informed and therefore spend the money more wisely. So the outcome of all that, because you're here to hear about making things. So in the African context, having done all of that, we kind of knew what types of projects would be coming up, where they were going to be built, what they were going to be making. So we could then spend a load of time developing. This is a digital library of very parametric physical components for building all these buildings. So again, that's the list of components you need to make endless different facilities all over the world, but you only need those components, and you can spend a lot of time optimizing those and making sure they do all the things you need. That is the packaged version of each of these. So all of these are designed to fit an ISO shipping container. So if you can make the thing in country, you send the files out, they make the bits, and off you go. If you can't, you can make it in the next nearest region where they can make the bits, put it in a shipping container, becomes a logistics problem, things come out of a box and they just get bolted together. It's called factory in a box. Each of those bits comes with its own assembly instructions, and each of those bits knows, for instance, it needs an M8, it needs a penny washer, nylock nut. So you can model a building and print out an instructions list, and you'll get like 1 million instructions, but you will build yourself an antibiotics factory or whatever it is. It will literally take you through step by step how to manufacture the building. This is antibiotics in Nigeria. So this is initial phase, that's where we think they'll end up. All of these components know when they've been moved around, so you can do all the sequencing and all the planning for the buildings. This is literally fabrication quality modelling. You would build the building directly off this. Jim, when he first modelled this, zoomed in and was saying we can't get that bracket less than £3. It's quite a nice bracket, but it's costing us £3. But that's the sort of conversation we're having in the office now. We are talking about component level design, component level manufacture. This, when you've modelled it, it knows how long it takes to build, it knows the cost, it knows the supply chain, it knows the logistics planning. We deconstruct these virtually and put the models into virtual shipping containers, which gives you a packing list of the actual things you need and the sequence in which you need them. So this now becomes a logistics problem that components turn up, they come out of the box, it's exactly the one they needed, they bolt it to the building. So some of these sites in Africa, you can imagine security is a problem. Things get nicked all the time. So the idea that things literally turn up just in time, get bolted onto the building, no one can nick it, that's really powerful. And again, it just becomes this assembly thing. To model this took 2 people 2 days now. So the speed with which we're churning these things out, because they literally get the brief, they go into that digital warehouse, they get the bits they need, they bolt them all together in the model, we're done, that's it. You can go and build that 2 days later. So that, again, that sort of speed of iteration is groovy. So out of that, we can then, because we're now talking about components, we're optimizing the components, we can start to really understand the supply chains. We are starting to go way below kind of tier 1, tier 2. We're now talking more directly to manufacturers. So all that overhead and profit, we're scrapping that because we're now designing individual components and going out to the best place in the world to make those components. So we can get incredibly good prices. We don't have to go to specialists now because the components are actually getting relatively simple. So our supply chain is massive because we don't need to talk to a proper steel fabricator. We can talk to the steel manufacturer and we do the least amount of post-processing on the steel. So again, this is driving that residual asset value right down. We do an awful lot of this sort of stuff. You've seen all sorts of examples. We do a lot of VR, firstly for the people that will build the building. So by the time they go on site, they've done all this before. They've kind of rehearsed it. Just looking at time. Yeah, it's all right. The other thing we do is we use this to induct people who will work in the building. So it's like the world's crappiest computer game that you come into the office, put the goggles on, you come in, you have to gown up and scrub up in the right sequence before you can go to the next stage, do the next thing before you go to your work face. So what it means is we get fantastic feedback. So people will work in the building for a shift and say, right, I could do the vision panel over there. I need to move that. So we start to get really rich feedback. From Glaxo's point of view, it means that when these buildings go live, like day one, they are fully operational. There's no learning curve because everyone's done it way before they got in the building. So we're training people up, maybe 18 months, a year before the building's actually complete. But as soon as they go into the building, they go, oh yeah, that's where I always go to work and that's where I always do my stuff. So we love a bit of prototyping. This was the obviously the model. This is the sort of thing we do in the factory now. This is a working GMP clean space, but it was built in our factory. This was then dismantled, reconfigured, and reused on a live project in the middle of one of Glaxo's sites. I've got some photos of that. This is, you've seen this kind of stuff. This is, we use Enscape, but that's just what the model looks like. So when you've got your VR goggles and you're walking around, that's the kind of quality of the imagery. There's no post-processing on that. Notice coloured components and brackets all over it. This is who built that. These guys are Gurkhas, so they're ex-British servicemen and women. They're not construction people. They've got no construction training. They've never built anything before. They can kill people, which is useful if it kicks off on site. But we took these guys, we trained them up in the model. They built a GMP working space. They build complex pharmaceutical facilities. So we've got in the UK this skills apocalypse coming because we haven't got, as mentioned in the last session, actually, we haven't got enough people. We've got an ageing population. We're about to lose a bunch of people. UK government has recognised that this is a massive problem, that we've got fewer and fewer skilled people. We've got an industry that's a bit crap, and then we've decided to build HS2 and HS3 and Crossrail 2 and Thames Tideway and Heathrow expansion, Hinkley Point, and 1 million homes. So we've got this massive problem. Government is taking this really seriously now, the idea that we are starting to have for a long time, low-skilled people that we upskill and train how to build these buildings, because we can do it we're actually getting the MOJ to build some bits of their own building to prove to them, the Ministry of Justice, how straightforward actually construction can be or assembly can be. These are some of the tricks we use. So in the model, all of those components know how all the trusses and things are linked. So one of the automated outputs is this color coding. So in the prototype, Jim of the coloured bracket fame went and painted these on himself. Now we print them on laminated strips and you just stick them on the truss. We then give the guys, these are the £3 brackets, we give them these brackets and say, right, if it's yellow, get a yellow bracket, purple bracket. So they just literally line up the colours, bolt the bits together. They don't stop to think, they don't stop to talk, they don't stop to measure anything. So all that thing I said about getting the right materials, the right things to the right people in the right sequence, that's what this looks like. We put data matrices on all the components. So we track every stage of the manufacture, packing, unpacking, location on site gets attached to that QR code, so we can track the entire quality assurance record for every component. The other thing we do is we attach standard operating procedures, again, like manufacturing, to those QR codes. So you heard earlier about Africa and they've gone straight, everything's on mobile, they've gone straight to mobile. So we get these sites where people can't read, but they've got a smartphone. So all they need to do is ping that QR code and it will say, right, next, get a friend, get a spanner. You're going to bolt the ceiling things together and off you go. And then we collect that data because we can see how quickly they're pinging the QR code, which means we can then start to post-process that and say, right, what are the steps that are taking too long? Can we take out an activity? Can we coordinate things better? Can we start to, this is proper continual improvement. So again, this is manufacturing's been doing standard operating procedures and constantly updating those and refining those as it goes. That's what this looks like in a construction context. I won't talk about that because we'll run out of time. And then this is, you can see QR codes on the components, the colour brackets. These bits, this is the walk-on clean space ceiling. These are all made at tabletop height. And then we literally lift the whole thing up and then it locks off and you put the ceiling things in, then you lift it up again. So no one works at height, no one goes on top of these things. Everything is done completely safely. When we did the prototype, we tested it with hydraulic jacks and then block and tackle, because in these African sites, they've all got block and tackle. And it takes ages on the block and tackle, but they like it because they can control it nicely. And yeah, it works like a flipping charm. That's a snapshot of the database. So this is one of those QR codes. This is all the things that are attached to that particular element. So you can imagine all that data then goes back into the model for the next facility. So I showed you that 2-day model that Jim and Jacob did of one of the facilities. The outputs where it says how long it'll take to build it, to put it together and all the rest of it, because it's all, we know that's what it takes because it's all based on the stuff we've done previously. So these are some of the stats. So yeah, it's quick, it's very quick. This, I think, is the killer. So 75% fewer people. They are then incredibly cheap people because they're not skilled craftsmen, they're not artisans, they are literally people we've trained up to do the thing, and then they are incredibly productive. So construction sites are normally 50, 60, if you're lucky, % productive. These guys are in the sort of high 80s, low 90s productivity. So the fact that you've got a very limited number of cheap, incredibly productive people, the labour saving is astronomical. And then it's about the same cost to build yourself a kind of world-class farm facility using this as it is to build a bit of a crap shed in Africa that will fall apart in 5 years. So yeah, Glax are very, very happy with this. This is, oh yeah, and I think one thing we like to think is actually the buildings that come out of this are still architecturally, I mean, they're incredibly high-functioning buildings, high-performing buildings, but we never lose sight of the fact that it's a piece of architecture, it's a piece of space-making. This is the one in Stevenage. So this is, we had to take the photos before they put the kit in. This is an active pharmaceutical plant in Stevenage. So API plants are That's the kind of heavy-duty bit of pharma. So when you take a tablet, there's only a few molecules of the magic stuff that actually works. The rest of it's all kind of sterile packing. So API is where they make the incredibly expensive, incredibly complex processes where they actually make the pharmaceutical stuff. This one was made in the middle of an existing facility, so it's the worst place in the world to work in some sense. This was effectively put together by Jim of the bracket fame and a tiny team of people who were cladding fitters. So again, we've gone right down the chain into the guys who typically bolt together glazing systems and said, you know what, you've got a spanner, you could build yourself a pharma facility. So you can see all the coloured bracketry in there. There was a little bit of obviously commissioning and things where we need some specialist people, but the vast, vast majority of this was built in the world's most complex site by a handful of people. There was no project manager, there was no tier 1, tier 2 contractors. It was literally one of our guys and a little handful of people in there. You can see Jim's famous bracket, but you can see all the colour coding. Highways. So we were brought in by Highways England a couple of years ago now to develop their BIM library, which is a reasonably standard sort of starting point for some of this work. So they said, look, can you make us a BIM library? We said, yeah, it's fine, but won't be exciting. We modelled kind of critically all of the operational and maintenance type phase, because people don't typically do that. So all of these library objects have every aspect of their maintenance and all the rest of it, and we've got the people, so we build in all the kind of clearance zones around them. We made them super parametric. So there's a whole team of people whose job it is to basically engineer every single one of these from scratch. So we think that's a big, when we talk about reducing design fees, we think that's a big problem in the industry, that there's lots of people whose job it is to just keep churning the same problem, the kind of bums on seats mentality. So we've said, look, not being funny, but why don't you just model it once, make it incredibly parametric, and then no one ever needs to do that again, which is making us unpopular with some of the other consultants. But obviously Highways love it because they've now got a very intelligent set of objects. We then put a load of those together as assemblies. So these are also super parametric. So when you drop in an ERA, it takes up the curvature of the road, it takes up the topography, it places all the signs that you need ahead of it, the right distance up the road, it checks the visibility displays and things. So again, this is the kind of automated design thing, the speed with which we drop these components, and it now is lightning fast. And then you can imagine, once you've got them, you can optimize them, you can turn them into a super DFMA, design for manufacture space. We developed a workflow. We found we couldn't get models of bits of the network quickly enough. So this is a workflow we developed. This model is made up of open source street mapping, Google Maps, some NASA geological satellite topography, British Geological Society. So this is literally put together by a little routine that goes onto the net, grabs a load of open source free data, bangs the components in, and then it's an infra works. So it's not perfect, but as a kind of 5-minute exercise, it's a pretty good starting point to then start layering in all the other information. So again, the speed with which we get from nothing to a pretty good functional model of the network is getting there. Then all of those components have been taught how they relate to each other. So a gantry knows that it needs a certain amount of visibility before you reach it. It knows how close it needs to be the next gantry. So all of these components are now nicely linked, so you can run an automated thing that just populates that model. So this is an exercise that would previously have taken a big team of people months to kind of potter along, dropping components and things. We'll now churn it in hours because all the components know how they're linked. We then have live modeling sessions. So before the session, we generate our base model, we put all our components in, and we then sit with people from every bit of the business. So rather than have the sort of, designer does some design, gives it the contractor who says, I wouldn't have designed that, reworks it, builds it and hands it over, and the operational people go, I wouldn't have built that, and then they start tweaking it. We get people who represent every bit of the life cycle in the room at the same time. You model it live in front of them, we shift the components around, we get to the end of it and go, right, so everyone's happy? Right, go and turn it into a much more sophisticated model, but that becomes then a fantastic brief for the next stage. So this is a poster that explains a rapid engineering workflow, that it does some early stage analysis, populates the components, does some outputs. We then have a collaborative modeling session tweak it, and at the end of that work, you get a fly-through, you get a model you can work with, we do some VR stuff, you get a complete stakeholder buy-in, and it takes hours now rather than months. These, I think, are just beautiful. This is some of the analysis that the computer does, where it's looking at the side grading, so it knows it doesn't want to place a gantry where there's a cliff face off the side of the road. It knows you don't want to be doing loads of cut and fill. So it will be looking for places where you've got the right sort of curvature, the road's flat enough, the gradient's okay, you've got good visibility, and this is some of the outputs from its kind of self-population activity, which is quite nice. We then, because it's the sort of thing we do, we said, yeah, that's interesting, but how do you know, highways, where to tackle on the network? Because we found out the contractors were saying that if they've got a choice between working on a big, long, straight bit of road or the nightmare junction, they'll do the big, long, straight bit every time. We're saying that's probably not where the problem was. So these are various outputs where we started bringing together loads of highways, different data, aggregating it, visualizing it, mapping it, and helping them to make better informed decisions. So we set ourselves a challenge of 3 clicks from network scale data down to individual components. So again, the sort of problems statement started to say, well, how do you tackle the highways network and how do you get into that problem? We then set up, this is for a live job on the M1, what we call production control room. So we now bring all this stuff together. So we've got a wall that has all the mapping data, all the mapping information, a whole load of data, and then the models are brought together. So when you go into the rooms, we've now got this complete interaction between working at kind of the GIS mapping scale, going and seeing what's happening in the data space. So we track everything that happens, all the activities, all of the orders. What we found, again, I think someone mentioned this yesterday, it started to completely change people's behaviors. So when we started doing this, contractors were going, like hell, I'm going to give you my information. Because part of their business model is to hold on to the stuff they've generated, ostensibly for the client. Once we started doing it, it started becoming really transparent who was providing data. There was almost sort of peer pressure forced on the people to then start to contribute their data. Then Tyler had that graph yesterday that showed the sort of improvement as people started to collaborate. Then people started to realize that actually the more data they contributed and everyone else contributed, the more benefit everyone got. So then people started slinging data at us. And then you start to get in a very, very different space where people are really interacting with it and then working through the models at the same time. So we have, this is what it looks like in operation. So this is when we first set it up. This is one of these collaborative sessions. So again, it's about the culture much more than it's about the technology, but the fact that people are interacting live with the data and the model, making better decisions, the speed of iterations rocketing. I'm going to speed up a bit. Right, Crossrail, I'll do this quickly. This is asset optimization. This is, I think, a really nice piece of asset optimization. So this is the Crossrail. It's the big east-west thing that goes under London. This is the architectural cladding, so what you see as a passenger. So this is a platform, say, and this is where the sail escalator comes down. We were brought in by Laing O'Rourke because they had to do a number of stations and they just didn't know how to build this. This is a classic non-constructible bit of kit. So this was the original design. We said actually the design intent is that face. Everything behind that we can chuck away because it doesn't make any difference to the design. All of these are GFRC panels, so all of these were mechanical lift, which is a flipping nightmare. It needed endless fixings because it was so heavy, so that's a health and safety apocalypse waiting to happen and a tolerance issue and all the rest of it. So we did a whole load of very, very detailed modelling. Bomb blast testing, if you ever get the chance to blow shit up, do it because it's dead interesting. To work out what was the thinnest thing. This is the optimization bit that I talked about earlier. So we got the weight of these down by 2/3, that's massive. These are all now a manually handleable bit of kit, which is nice. Number of fixings down by a factor of 24. So imagine all of the tolerance things and health and safety things and all the problems you're about to have. And then way fewer components, which is nice. This is how we did it. So the tunnel, it's not like the one you saw earlier. It's sprayed concrete, so it's all over the place. And obviously they've woven this thing under London, so it's had loads of constraints around it. So we said, look, what you don't want to really do is touch the tunnel. So we'll put in this rail, and we'll get that absolutely perfectly aligned in space. We'll do the same thing on these bits at the bottom. And then we don't ever touch the tunnel again, because now I've got rid of all my tolerance problems, because I've now got absolutely fixed points in space that I can fix the panels to. In the smaller tunnels, we don't even touch the tunnel. It just sits on the platform. We've then got a model. We literally model every single nut, bolt, screw, washer, like everything that happens is in the model. We make these ladder frames, because that's a fixed point and that's a fixed point. You make this ladder frame and it wobbles about a bit. So we rejig all of these points, put these little pegs in, and then they're sort of mass customized for that specific instance. But what it means is all of these are now perfectly aligned in space, so we don't need any adjustment on these. So on the original design, I've got a wardrobe at home that I've never managed to get the doors to be perfectly straight. There's millions of these panels. So we said, what you want is zero adjustment. One of the tests for this was that Crossrail said you had to be able to strip one of these off, get behind it, do some work, and put it back within 8 hours, because overnight we might plausibly have 8 hours to do some maintenance work. When we did the prototype, they did it in 32 minutes, because there's no adjustment. We found out afterwards, actually, they'd loosened all the screws a little bit. So it might have been 34 minutes, but everyone thought 8 hours was going to be a challenge, so when they're doing it in half an hour, that's gold dust. This thing I will talk about in a bit, that's called a tusk. So these are all standard components. These are largely bespoke, because they take up, wherever they've just had to weave the tunnels through there, the connecting bits, they're quite nice. So we've got a SolidWorks model, Autodesk, we've got a SolidWorks model that operates at the level of the Crossrail tunnel system, right down to, I literally mean every single washer, nut, bolt, screw, the whole thing is in there. This model talks to the SAP system, so it controls procurement, it talks logistics, it talks to sequencing. Everything is now done completely through that model. It's a very, very digital workflow. That's a mold for that tusk. That is CNC milled directly from the model, because you couldn't do enough drawings to describe that thing. So the fact they're all a bit different and bespoke doesn't matter, because the computer doesn't care. It takes up the shape. CNC mills the mold, and then these things are coming out, and they're absolutely perfect. I'll sort of speed over that. You can imagine we're sort of tracking every component. We're doing some nice Dynamo workflows to check the fit. So that's a nightmare. So I was saying to you on it, that doesn't look good. What's the scale on that? So it's out by, you can't read that, 1.5 mm. So that's about, 300 meters long, and we're out by 1.5 mm at that scale on that project, which is, that's smooth. I'll skip over that bit. So we've now got a really nice workflow where the point cloud survey comes to us from the as-built tunnel. Turns out it's not where anyone thought it was. Maybe not surprising, and it's a bit out of tolerance, which is maybe not surprising. But you can imagine the change order that would have come in if day one they'd put the first panel in and gone, doesn't fit. It would have been a disaster. So we've now got a workflow that runs an automated check on the point cloud survey, colors all the components and says where it's in tolerance, out of tolerance, what you need to do. That then goes to a guy with an iPad who marks it up. Then you scabble it. And then it means that these bits are fitting absolutely perfectly. We designed the lifting frame. We did the swept path analysis to check that you could get the components in, you could get them around, you can get them to site. We plan all the logistics, all the sequencing as per the GSK stuff. And these things are absolutely flying up. This was probably a couple of months ago, but you can see these are going to be absolutely beautiful bits of kit when you get down there. And everyone assumed the limiting factor would be how quickly you can do them. Now the limiting factor is how quickly the factory can make them, because the guys are just channeling these things up. We've heard virtually nothing from the second station, because no one has any questions. No one rings us up to say, what about this and what about this? Everything's been pre-resolved. Even the setting out now is automated via the model. So the model talks to a little robot that runs along, pings a couple of laser points, and does all the setting out points. So we used to give them a whole load of setting out dimensions. Now we don't bother. The computer does it itself, or the thing does it itself. So it's incredibly automated. It's incredibly productive, and it's quite sweet. Last thing I'll talk about, because I'm actually over time. We do tons of work with the central government. So I'm part of the BIM Level 2 working group, Digital Built Britain, which is BIM Level 3. So as I say, government can see this coming out. It's got a massive problem with all the things it's got to build and the inability of the industry. We literally don't think the industry can physically build all the things we need to do in the next 5-10 years. So we were brought in, or we were asked to write a sort of strategy document. This isn't, it will be on our website next week, actually, if anyone's interested and wants to read it. There'll be a link to it, and it'll go on the Digital Built Britain website at some point. What we said, and I think this is sort of Tyler's point from yesterday, no one gets into this proper manufacturing space, because even the big programs, so prisons is about £1 billion, schools is about £4 billion a year, highways is a few billion. At the moment, government sort of buys some prisons and buys some schools and buys some hospitals and all the rest of it. We were saying what you should do is aggregate that spend and start buying components, because at the moment, no one ever gets over that barrier because no one's really got the investment to do a proper manufactured solution. So if you aggregated your £10 billion spend, you could get yourselves into that space. So we said, this is what you do at the moment. You as the client, you get a PM who assembles a design team, who gets a main contractor who, in our experience, contractors don't actually have anyone directly employed. They basically have a phone book. So they then call their specialists who call these guys, and this is where the magic happens. So when we're building buildings, these are the guys we want to be talking to. What we said you should do, and you can see this is exactly what highways are doing, this is what Glaxo are doing, this is what prisons are doing, is you should own your digital components, and you should have a known supply chain, or be able to go to such a wide supply chain that you can smash these things. Give them to suppliers and design teams who configure those components as schools and hospitals and. We said every space that anyone ever needs lives on that graph somewhere. So there's only so many clear spans you ever need, and there's only so many clear heights you ever need. And then there's levels of how standard or variable and simple and complex the buildings are, which starts to tell us something about the mass customization-ness of the components and all the rest of it. So we hypothesized that with a few platforms, so just in the way that every BMW car uses exactly the same platform. So some cars have got too good a chassis, but it doesn't matter because it wasn't worth the bother of making a less good chassis. We said if you had a sort of housing system, general office type system, and you've got a kind of big space system, that's most of the things that you would need to buy. If you were then buying loads of them, then you could really get into optimizing those. You could really get into understand the supply chain. You would start to get incredibly good at assembling buildings using known methodology, and you could start to upskill people and all the rest of it. This one, we've developed all of these. The Glaxo one kind of sits in there. We've got another one we're developing. We've got a housing one we're prototyping at the moment, and we've got this one we're prototyping at the moment. This one we're going to open source to see what happens. So we're going to make it, test it, validate it, prototype it, get all the digital things, and then put it out in the world. So we hear people talking about this sort of exciting new world where imagine we were all working in a open source collaborative environment and we could build anything we wanted with components that we could get off the internet. My 7-year-old will go, what, like Minecraft? I'm already doing that today. So we're trying to cultivate that sort of culture where we're going to make these components available. Hopefully what will happen is people will start to pick them up and start to use them and refine them, improve them, and find the other bits that we need. The supply chain will start to respond and say, actually, I could make loads of those. Government is taking this really seriously now. They've sort of adopted that book as part of their sort of strategy for sorting out construction. We're doing the big prison estates transformation program at the moment. So we said there's two things we'll investigate. The problem statement was how do you reduce reoffending? So reoffending costs the UK taxpayer £13 billion a year at the moment. So there's people coming out of prison, they don't know how to cope, they can't sort themselves out, they fall back into crime, they come back into prison. We're saying, the first year, we spent just understanding what would create a rehabilitative environment. So this was effectively chip thinking for prisons to work out what a new prison estate would be like. I can't show you any of the outputs for fairly obvious reasons, but we've now got a very different design for a prison, which should be much more rehabilitative. And then we said, right, now we've got that, now we're going to work out what's the quickest, cheapest way you can possibly build these things. So these on the metrics, you can see a very similar graph. We said you probably need 4 platform systems. You need one for the house block accommodation, one for most of the other spaces, so where you've got offices and classrooms and other things. You need a sort of big space, architectural space, and then you need a big sort of general space. What we found is that about 80% of that. So that's about £1 billion. Needs 2 platforms that we're currently prototyping. We will design the life out of these things. But you can imagine if you're going to buy £1 billion worth of stuff, you can put a huge amount of effort into really optimizing it, exploding the supply chain, really getting into the detail. This, I think, is really powerful. So the metric so far we're getting is that the labour component needs to be about 60% low-skilled people that we've trained, and quite a bit of supervision. We'll put in the first ones, and then only a few skilled people for some of the electrical things and commissioning and crane drivers and some of the other bits. So we reckon of the £1.3 billion, a massive chunk of it is going to be low-skilled labour. So this is apprentices, this is local people that we'll employ to build their local prison. So that's a fantastic and good news story from the government's point of view, that even before the prisons open, it will be pumping money into the local economy because we'll be getting local people to build this. The other thing which is possible, which we're having very serious conversations about at the moment, is that we can get prison labour. They already have some manufacturing capability. We can get them to make some of the components for these. So that is a fantastic good news story, because firstly, the cost of construction plummets because we've got people that are very cheap because they're in prison. But the real trick is that you use that construction program to teach them about manufacturing and warehousing and logistics and basic assembly. So they come out of prison, they're less likely to reoffend because you've taught them some skills. So straight away, again, forget your construction cost. If you can lower that £13 billion, that's magic. And we're tying together this delivery with the Heathrow expansion programme, and then the schools programme, and then presumably Crossrail 2 and HS2, all the rest of it. So you start to get a pipeline of projects using some of the same components, using the same methodology. So suddenly you get this kind of long-term plan of going, well, actually, let's engage local people, low-skilled people, let's engage prisoners. They'll be less likely to reoffend, and they will build the next generation of infrastructure. You've sorted out the skills gap. You've created manufacturing capability for UK. You've changed the way you deliver major infrastructure projects. And it's potentially a fantastic good news story. So hopefully, with, as I say, prototyping this now, we'll be on the site with the first ones early next year, Q1, Q2 next year. So if you're interested, then keep tabs on that, because it might be very exciting. So I've massively overrun, apologies for that, but I've flown halfway around the world, so I thought I might as well show you a few things. Those are my details. Adam Jordan, who's sitting at the front, Adam heads up our Asia Pacific office, so he splits his time between Sydney and Singapore. So if any of this is of interest and he wants to follow up, then by all means contact myself or speak to Adam. The book should be on the website next week at some point, and yeah, I'll shut up now because I've taken too much of your time. So thank you very much.
Thanks, Jamie.